Same questions. What do you remember from yesterday? Anyone want to volunteer? Anything that you remember from yesterday? Yes, very good. So what do you remember from manufacturing? Yeah. So hand layup, very good. Spray. Filament winding, very good. Sizing, very good. And then pultrusion, very good. So you remember how the glass fiber is made? Just interesting, right? Okay.
What is micromechanics? We were not playing it. The meaning of micromechanics. We came to know study of separate fibers.
Right, right. So you have properties of the fiber, properties of the matrix. If you combine the two using the properties of each material, you get the combined properties, and that's what is known as micro. Very good, thank you.
Due to microbuckling, we cannot use fiber.
Thank you. That's good. That I didn't mention that. I mean, I mentioned it, but it's in the notes. So good point. Microbuckling. Because of microbuckling, we cannot use it for compression member. Anything else?
We derived formulas. Mathematical engineering.
Yes. Yes. If you want to remember anything from micromechanics, remember rule of mixtures. Huh? Yeah, that's a good one to remember. Anything else? Okay. So properties are, you have, if you can remember, it's a good thing to remember what kind of properties we can get in composites. Yes, we will talk about statistical. Guaranteed strength. Yes, absolutely. Yeah. Okay. So quiz. Go through quiz. First one, strengthening of round bridge concrete columns, wet layup method is well suited. True or false? True. I mean, it can be true or false. If I don't seem to like the answer for true, you say, okay, false. No, but why? Why is it true or false? Yes, wrapping has to be done manually. Of course, you can do robotic, but that's also wet layup only. So, wet layup is well suited. So, that's a yes. It's true. Okay? Very good. Transverse strength and transverse modulus of composite are matrix dominated? Very good. True. That's correct. The longitudinal strength and longitudinal modulus, they are governed by fiber. Transverse strength, transverse modulus, everything is governed by matrix. Very good. If a tensile strength of fiber is 1200 MPa, I just picked a number, okay? A composite plate using that fiber can be designed to achieve a tensile strength of 1200 MPa. True or false? Why? So we will have some matrix. So that matrix will reduce the strength. So you can never ever achieve 1200 MPa. Okay? Very good. It's possible to use compressive strength of FRP bars in concrete column design. False. We know that. Sizing of the fibers is the process of finding out the diameter of the fiber. Very good. It's false. It's not true. Sizing is a coating. Okay? Very good. So, can anyone explain what polymerization is? Just one simple sentence, that's all.
It's a chemical reaction between the resin and the
Right. It's between two parts of resin. So once you start the chemical process, it's irreversible. The chemical process is completed by what's known as polymerization. Very good. Rule of mixtures.
The properties of the matrix composites by means of based on gate basis.
Right. But your one other important thing is missing. Yeah? right, but there is something missing.
So assume strain is same in fiber and matrix.
That's correct, but I am talking in general. What is rule of mixtures? What you said is right, but it's not completely right. Like there is something missing. I'm sorry.
Total volume of composite is.
Yeah, that's where you apply, but there's something missing in our definition here. We did not mention one thing.
Minimum being 4.
No, that is something else. Yeah, we are talking about rule of mixtures.
Heterogeneous to homogeneous.
Volume tension maybe.
Yeah, complete your sentence. Yes, thank you. That's the key word. In proportion. It's in proportion to the relative properties of each material. That's what is rule of mixture. Okay, that's correct. In proportion. That's the key word. Okay, filament winding. Of course, you know what's filament winding. Created tube or something like that.
Surface of resolution.
Yes. So we just wrap this fiber, wet fiber, around an angle, and when it sets, we get filament wound particles or parts. Micromechanics. We already talked about micromechanics. So micromechanics is simple. What is RVE? RVE representative volume. What is it?
Smallest volume of matters which represents the whole.
Very good, very good. So if you have a composite section, the smallest volume of the composite that represents the entire composite property. So that's, you can consider one fiber and the surrounding matrix, and that will give you RVE. So if you consider the properties of that RVE, that's as good as the properties of the entire composite. Excellent. Very good. So that's RVE. Okay, did anyone of you try using this Excel spreadsheet? Was that all right? Oh, you didn't get it. Excel spreadsheet. Oh, sorry. We will send it. Sorry. All that you have to do in this is plug in the numbers. We'll send it to you, okay? So all that you have to do is plug in the numbers in yellow cells, okay? If you want to enter the numbers in any other cell, it won't let you do it because I protected it. So you don't, by mistake you won't mess up anything. So, okay, we'll send that. So that's good. Any questions from yesterday? So today we will first start with design philosophy. Dr. Das asked me specifically to tie IS 456 specifications with ACI specification, because I am presenting ACI specifications, right? So some of you may not be familiar with those specifications. So how do they tie with IS 446 specifications, for example? So I'll spend a lot of time tying the two together, because if at the moment there is no design guideline for IS or Indian standard compatible guidelines. So if you are designing, some of you, I know you said you are going to design some stuff. If you are designing to ACI, just designing it using ACI document may become a little bit unsafe. Okay, let me not put it as unsafe, but it won't be consistent with your IS 456. Can you hear me? I don't think so. Can you hear me now? Shiv Prasad? Very good. Thank you. So can you hear me now? Okay. Very good. So first we'll start with general considerations. Just what are the differences? So we will use, in both codes, we will use equilibrium, compatibility, and of course stress strain curves of the materials and stuff like that. That's what we will use. And then FRP bars and concrete individually show brittle behavior, therefore FRP rupture or concrete crushing is considered to be a governing mechanism. Okay, that's something I mentioned many times and some of you picked it up on your own. So what we are saying is FRP has linear stress strain curve. Therefore, we don't know if there is some under strength of FRP material. Then if we design it to go all the way up to the failure, then it can fail in a brittle manner, right? So that's the reason we try to reduce the allowable FRP by guaranteed strength and stuff like that. And then we will design the section to fail by concrete crushing. So in steel reinforced concrete, we don't do that. We use under reinforced condition. I don't know if you noticed that, but your IS 456 requirements automatically ensure that you are designing your members to be under reinforced. Okay, so that's a deviation. So FRP reinforced beams will almost always be designed as over reinforced beams. So it's also preferred because even though concrete crushing causes something which is not ductile, that means it's not the beam failure is not ductile, but still that is more preferred than sudden snapping of FRP bar. Okay, that's the basis. So compression controlled or tension controlled mode of failure are still allowed. Both I didn't define what compression controlled and tension controlled failures are. We'll do that. ACI refers to compression controlled and tension controlled condition. I'll define that today. And of course, fire and temperature are always a problem. So whenever you are designing in limit state design, you have whole set of loadings and another set of strengths, right? So if you say, let's say you are designing a test and you are testing 25 specimens. Some of the specimens may fail at 100 units, some may fail at 80, some may fail at 70, some may fail at 120. So just taking the average is not good enough. You have to also make sure there is some amount of reliability in your data. So what we do, yesterday I already mentioned this, we will shift this line and this is your loading line or curve for loading. This is the curve for strength. My strength always needs to be greater than, on the x-axis we have loads, right? Load or strength. On the y-axis we have frequency. So my strength always needs to be greater than the average loading, right? So the area under this curve, you know this, I am just mentioning it again. Area under this curve is the probability of failure, the common area under the two curves. So larger the area, larger the probability of failure. Smaller the area, smaller the chance or probability of failure. So if I move this all the way to here, do you think this area under the two curves will be small? It will be small. Can it be 0? Statistically it can never be 0, right? So even if I move this significantly to the right hand side, that means the strength of the element or member or material is increased substantially, this probability of failure will never be 0. That is statistically speaking. So we said, what is acceptable probability of failure? And yesterday I mentioned 1 in a 10 million chance is something we are already used to. Without knowing, we are able to accept a probability of failure of 1 in 10 million. So every time you start your car, there is a 1 in 10 million chance of getting into an accident. So that is something we are accepting. Therefore, we will make sure we have a probability of failure which is compatible with other activities of life. So to do that, we use in ACI 318, which is the design code for structural concrete. So American Concrete Institute design code for structural concrete. We have a phi factor here, and nominal strength, N stands, subscript N stands for nominal strength. U is the required strength or the factor load effect. Both are the same. U is the required strength. This is the design strength. When you add phi factor with Sn, that becomes your design strength. Sn by itself is nominal strength. Okay. So unlike in IS 456, which is following British standards, the American standards apply one factor, strength. This phi is known as strength reduction factor, and that strength reduction factor is applied to, for each type of action, there is one strength reduction factor. I'll show you what those are in a minute. So strength reduction factor, so what do you think strength reduction factor is? Is it going to be more than 1 or less than 1? Less than 1. Perfect. So we are trying to, remember, go back to these bell curves. So when you have a normal distribution, we are saying, even though my strength is, average strength is here, I would like to make sure it's slightly onto the right hand side. So we are minimizing this probability of failure. Same thing for what about the loads? These loads, just like in IS 875, I think, is the loading standard. So in that we have load factors. Similarly, ACI also has load factors that are dependent on ASCE 07. ASCE 07. That's the loading standard for American designs. Many actually, this is interesting. Lot of designs in some design companies, they are actually designing for American conditions. I'm sorry. Okay, so they are sitting in Delhi or wherever, Bombay or wherever, Mumbai, and they are actually designing for American companies. So they are using ACI codes and stuff like that. So that there is a lot of potential for that, market for that kind of work in consulting work in US. So I know this because I have seen some forums where they are saying they have some questions, people reply and clarify the design requirements for ACI. So phi Sn is the design strength. So the difference is nominal strength, which doesn't have a phi factor, design strength, which includes phi factor. So moment you apply this phi factor, which is less than 1, this value is smaller, and with factored loads are imaginary loads. They are not real loads, right? So factored loads are imaginary loads, assuming that there can be overloading on the structure. You apply those loads. So you are increasing the loads on the load side of the equation, and on the strength side of the equation you are decreasing the usable strength. That's how you are able to get factor of safety. They don't call it factor of safety anymore. No one, at least in American context, they don't. So design strength, I mentioned this. Design strength is strength reduction factor phi times nominal strength Sn. All the phi factors are less than 1. You must find out your design strength based on material properties, stresses, and mode of failures. things like that. So factor loads are always.
This type.
Oh, okay.
Slide change. Slide change.
Yeah, I can use that. Sorry. So, all right. So the load factors are greater than 1 almost always. Of course, in some cases it's 0.9 to ensure factor of safety. So factored loads are notation of factor loads will have some subscript u. So mu, vu, pu is factor load moment, factor load shear, factor load axial force at a section, and you must use, you know this really well. So the required strength is what is factor load effect. Factor loads will always be greater than factor loads will always, or factor load effects will always be greater than the service load effects. That's what I mean. So this is what we use in ACI. So this is very important. The reason it is important is I'll bring it out in next 10 minutes. So if D for, this is very, I mean you can just guess this. D is for dead loads, L is for live loads, L sub R is for roof loads, S is for snow loads, R is for rain loads. Okay. So you have 1.4 times dead load. If your dead load is dominating your design, that's what you will govern your design, but most likely not. Then you have 1.2 dead load and 1.6 live load. So in Indian standard, what do we use here? 1.5 and 1.5, right? See, there is a big difference. I will show the numbers in a minute. So, but in American context, they use 1.2 here for dead load, 1.6 with live load. If you have roof load, you can pick the larger of the three and add it to, or multiply by 0.5. So this is normally dominated by live load. And of course, there are other combinations for earthquake loads and wind loads, okay? So that's how there is a difference. That's what I mean to say. What about phi factors? Phi factors for bending, they vary from 0.65 to 0.9. So if it is brittle failure over reinforced condition, you use 0.65, which is not allowed, by the way. So if you are doing a new design, you are not allowed to design the member to be over reinforced. However, you will come across some designs where the situation is already over reinforced, like existing structures. You are doing a repair work or rehabilitation work. There you have not designed it, and the designs were done like 20-30 years back when there was no requirement that it has to be under reinforced section. For those things you may have to use over reinforced condition just for consistent with the existing design. But any new design you cannot use over reinforced section for steel reinforced concrete. We are talking about steel reinforced concrete at this time. It's very important for us to understand the differences before you start using ACI 440 for FRP design. Okay, so columns with ties, just ties, 0.65, columns with spirals, 0.75, just like in Indian standard, there is in ACI standard, there is a minimum volume of ties required, spirals required, and if you don't have that much minimum volume of spirals, you cannot use 0.75, you have to use 0.65, phi of 0.65. So it must be, or the columns must have adequate spirals to satisfy the requirement for volume of spiral within one spacing, and if it satisfies, use 0.75, which is larger phi factor than 0.65. So beam columns, it's probably 0.65 to 0.9 with ties. If it is with good with adequate spirals, it can be 0.75 to 0.9. Beam shear and torsion, everything related to shear and torsion, 0.75. Bearing on concrete, 0.65. Okay, so finally we need to make sure phi Pn, phi P sub n is greater than P sub u. So phi Pn is the design axial load strength, P sub u is the factored load acting in axial direction. Same thing with shear, phi Vn should be greater than V sub u. Bending moment, for bending moment you must make sure design bending moment strength, phi Mn is greater than M sub u. This is very straightforward, right? Only difference is in case of IS 456 we use material factors, safety factors for material, that's what I think it is called. Okay, so I'll just run you through this. You probably know this really well, but I just want to show you the differences. In case of IS 456 we use factors of 1.5 dead load, 1.5 live load. In case of wind dominated loading, 1.5 dead load plus 1.5 wind load, so on and so forth. Okay, now this is a deviation, like ACI and this requirement, they don't match. So if sigma D is design strength of the material equals sigma K, which is characteristic strength of the material, sigma K, and mu M is partial safety factor for the material. For concrete you have a 0.67 already with characteristic strength plus 1.7. So this is 0.446. That's a very it's a low value actually, relative to ACI. And in addition to that, you also have for steel 13% premium, that's 1.15 factor. So you are adding one factor to concrete, and also we are adding one more factor to steel. Whereas in case of ACI, we don't add individual material factors. We